Okay, let's start. Well, of course, just a reminder, next Monday at 5, you're supposed to be live in person for test 3, and you have to go to Marshak room 3. Incidentally, for the final on December 15th, you don't come to Marshak, you come to Baskerville. They have a room number there. You go to a particular room in Baskerville. All right. I will remind you when the time comes. But on Monday at 5, you check in, and the TA will check you in so that you will then be, checked in as live. And if you are not live, your Blackboard grade will not count. And I will allow for 10 minutes for this process of checking in so that the Blackboard exam will come on at 5:10, and it will be for an hour and 15 minutes. And the format is the same. Somebody had a question. Oh, what was the average? Gee, I never said what the average was. The grader graded it, and the average was 80 something. Let me see. Let me see if I have it here. Oh no, I'll download it. Just 1 second. No. Gee, what happened here? I had to restart my computer. That's why I don't have it here. Oh no, the average is 96. The TA, he kind of gave partial credit for this and that. It's 96 is the average score out of 150, right? Yeah. Okay. And let me see, what was I going to say? It's the same format, random block, and within each block there will be maybe multiple answers, which is basically like multiple choice, except it has the formulas associated with it. What was the thing about what? The room changes for the final, not for Monday. Sorry, maybe I shouldn't even have mentioned Baskerville. The room changes only for the final. All right. Now I have not curved it for exam 2. So all you need to know is what is your average relative to exam 2. And what you want is to try to say, gee, last time I didn't do so well relative to the average. Now I want to do better. And as I keep reminding everybody, I track this ratio R on how your performance is from test to test. And if you indeed did do enough of this exercise, and I cannot say enough about this, that you have to get your concept clear. Like, is this asking about time dilation? Is this asking about Lorentz contraction? And then if you grasp that, then you have to let your algebra, your trigonometry be strong enough to now say, okay, I take this equation, but now I got to do a little algebra on it because this nasty professor didn't ask for the actual time dilation. He was asking what was the velocity that caused this time dilation. So I have to do a little bit of algebra. Well, you need to be strong enough with the algebra. I cannot help you with algebra if you are not that strong. So you then be able to, okay, say, oh, the fact that you got this, extra time because of time dilation, well, that means that you were actually flying through space at, half the speed of light or 3/4 of the speed of light and so on. Okay, so you need to be first grasp and say, what is this question involved? And then to now use that algebra to now say, this question asks for something else, but I can work from this equation and figure out that something else. Okay? Any other questions or comments? I mean, I have said it enough times, but it's the same. Oh, final is also the same format. It's just that final would have more questions because the time is double, more than double. Okay? All right. Okay. So now I want to remind you this thing about the twin paradox because that is dealing with time dilation, and the people who really are interested in the full aspect of Einstein's theory of relativity, they actually do consider what is known as a paradox. Now, what's that paradox? Paradox is, as we already saw the cartoon, you had enough money to pay for a space flight, but your cousin did not. So you say, okay, I say farewell to you, bye bye, just until we meet again. So you go into here and you then lift it off. Your cousin just knows that it lifted off at 5 p.m. Eastern Standard Time, and there was this, your spaceship went off, and your spaceship went to some Alpha Centauri, some galaxy somewhere. And we know the distance from the Earth to Alpha Centauri, which is so many light years, and you are traveling at a certain speed, whatever is that speed, and you now were on that all the way, and actually you had to accelerate at the beginning, and then you went on the cruise control, so it was at a steady uniform velocity, and then you have to decelerate, turn around and come back. So there is some extra general relativity issues to be taken care of, but we don't need to worry about it. That's just a small short segment. The rest of the time, so many years, is just simply at constant speed. And you now say, okay, I went there and I came back. So you now came back. But of course, since it is so far away and you are not going at exactly the speed of light, because within the light year means that it would take light so many years to reach Alpha Centauri. But your spaceship does not go at the speed of light. It probably goes at 0.2 or 0.3 or 0.4. So by the time you come back, your cousin is no longer young. Yes, your cousin is no longer young. But you come out and you say, what's the problem? You come out and you say, hey, yeah, I'm back. But you are maybe only 2 years younger. But your cousin is now maybe 20 years younger, 30 years younger. So that is that twin paradox, which is in principle a real thing. And these scientists, they have actually subjected Einstein's theory of relativity, including general relativity effects, and there has been no deviation from Einstein's theory of general relativity. All right, so this is just to give you like an application of this time dilation, and there is another way to look at that. And I would want to, since you are biomed people, if I am the astronaut and I'm on space, my heart keeps beating, right? Does my heart rate depend on, ooh, you're going at 30 miles per hour, your heart rate, or you are now going at the 0.2 times the speed of light, your heart rate is different. We are not talking about, oh, I got scared of something, then my heart rate may go up. That's because of my body reaction to seeing things. But you are now on a uniform, straight velocity at whatever is your speed, but the spacecraft is not trembling even as it goes. The spacecraft is going smooth. It's in an inertial reference frame. It's going at exactly whatever, 0.2 times the speed of light. Your heart is pumping, but your heart is pumping according to whatever is your body, metabolism. Some people, their heart rate is higher. I don't know. They have a V8 engine in there. So their heart is always going at 70 or whatever is the pulse rate. But my heart rate, maybe I have a V4 engine. My heart is, beating slower. Whatever it is, my heart rate continues at the normal metabolism. So my knowledge of time is not affected by the fact that I'm on a spacecraft. But now on the spacecraft, I will say Alpha Centauri is not that far away. Why? You remember we also learned about Lorentz contraction? You say on Earth that it is 2.8 light years away, very, very far away. So that's what you call the distance. But me, I say, well, it actually is now shorter according to Einstein's theory of relativity. It is now shorter by square root of 1 minus v squared over c squared. Right? That's the thing that came from Einstein's theory of relativity, right? And so you now say, well, it is not so far, 2.7 or 2.8 light years away. It is shorter because my velocity is high. It appears to me to be shorter. And my heart continues to beat the same way. And therefore, I would be older by a smaller amount. Whereas you, my cousin on Earth, you say, I had to wait because you are, going to Alpha Centauri. Alpha Centauri already is 2.8, 2.7 light years away, and you are only going at 0.2 the speed of light. Oh, it takes you so many years. Well, your cousin's heart rate is on Earth. He continues to beat whatever it is, and then he says, you took a long time coming back. But when you came back, you say, what's the problem? It only took me so many years according to my clock. So this is that twin paradox that involves both time dilation and Lorentz contraction. Are you sort of beginning to grasp? We don't need to put in the formulas. We are not going to ask for formulas because what I wanted to kind of stress is Einstein's theory of relativity has many cute Gedanken experiments, has many cute thought experiments to kind of tickle your curiosity, provided that you take the basic postulate, which is that the speed of light is the same however fast you are going, that the speed of light remains 2.9979 something or other times 10 to the 8. Can somebody read what was the question? The chat disappeared. What was the question?
Professor,
Somebody read it.
I was just wondering, like, for the twin, like who goes to space, like for
Yeah.
him to not age, like does spaceship has to travel like with the speed of light? Like, is that a requirement?
Yeah. Namely, for that time dilation to be noticeable, your spaceship has to go very fast, like 0.2. Because if your spaceship only goes at 100 miles per hour, 2,000 miles per hour, That is nothing compared with the velocity of light. So this square root of 1 minus v squared over c squared is basically 1, right? Because your v is so small relative to c, because c is so fast. So if you say, I fly on the airplane, what is the time dilation? Oh, it's very, very, very small. And yet, in 1972, there were some of these engineers who want to test the atomic clock, the accuracy of the atomic clock. They actually flew a plane all around the Earth, and then they say, gee, after I fly around, there should be a time dilation of 0.00000000000 something seconds. And then they have an atomic clock, and they could then say, yeah, I did measure, and it was 0.000000000 so many seconds. You understand what I'm saying? There are these fussy people, I mean, because they have the resources, and they actually wanted to check this time dilation by going on a commercial plane, hopping around the world, and have a very accurate atomic clock to figure out what is the dilation, even though the dilation is only 0.0000000 because your velocity of the airplane is so small relative to the speed of light. Does that answer your question? Okay. And this is why it's called Gedanken experiment, because of course, to this day, there is no astronaut who actually took the flight with a speed of spaceship around 0.2 to go to Alpha Centauri and came back. It's in, because it's not in our lifetime, not in anybody's lifetime. Okay. All right. Now, next, I want to sort of remind this thing about relativity. It is this thing called simultaneity. Here I use a non-relativistic example, but relativistic example will come with a very interesting paradox, which I will again spend a little time on. You're not going to be tested on this, so don't be so tense, okay? But you need to know applications of time dilation that we already did, and applications with Lorentz contraction, which we did earlier on Monday. Now I want to sort of fill you in on things that make you appreciate more what Einstein did for curiosity, for Gedanken. Now, if I have somebody in a train and he or she is right in the middle, he can in fact send a light signal or a whatever, laser beam, right? And well, in this case, it's not a laser beam because it took 1 second. So maybe he throws the ball. He throws 2 balls, one backward, one forward, but the same speed. If he throws a ball with the same speed forward and backward, this ball will reach this one at time t equal to 2 seconds later, and this ball will reach this one 2 seconds later. Why? Because he or she was exactly in the middle. And then he or she will say it hit the front and the back of the train simultaneously. Right? You know the word simultaneous? Simultaneous means it was at exactly the same time. Now, how do you know it was simultaneous? Well, that's because there is a clock here and there's a clock there, and they have been synced. They have already been synced to, let's say, like the computer, we are synced. My computer says 5:21 p.m. I assume that your laptop will also say 5:21 p.m. So the clock here and the clock here, they have been synced. And then the clock will go ding when the ball hits. And the clock here will go ding when the ball hits. But since it both came from the middle with the same speed, one forward, one backward, this event and that event, you say, is simultaneous. right? That's simultaneity. It is viewed from the train. All right. Are you okay with this concept of simultaneity? Because I'm in the middle. I made sure I made all of the measurements. I want to be exactly in the middle, and then I throw off two, balls with the same speed. Namely, I shoot the dart, the same toy gun. So it is the same speed, and now it hit the back end and the front end at the same time. But now your friend who is on the platform, your friend at the platform will say, wait a minute, wait a minute. You did throw two balls, but because you are moving, the back end of the train is rushing to meet your ball, right? Because you threw the ball is flying through the air now, but your back end is rushing towards the ball, whereas the front end is running away from the ball, isn't it? I mean, it's clear. This picture is drawn to emphasize that point. And therefore, this ball will hit the back end first before the other one hits the front end. You got the picture now? And so you say simultaneity. Oh, this is not simultaneous. Simultaneity depends on the reference frame. The simultaneity of events. Now this is two events. One event, this ball bang against this back, and the other event was this ball bang against the front. These two events, from the point of view of the train itself, because you made sure that you were in the middle, it would bang and bang at the same time, simultaneous. But now your friend on the platform will say, no, 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 it cannot be. I actually saw that your back end was rushing towards to meet this ball. Therefore, this will hit first before that. All right. And now we can have fun with simultaneity, Lorentz contraction, and the time dilation. Basically with Lorentz contraction. Are you ready for the next slide? Okay. All right. Now, there's this thing called train trapped in a tunnel paradox. And this is to test on the Lorentz contraction. And then in the end, we'll discover, oh, there's also simultaneity in there. Question of simultaneity. All right, we have a tunnel that is, let's say, 800 feet long. In its rest frame, namely on the ground, right? Because after all, I built a tunnel and I know that the tunnel, of course, the tunnel, Lincoln Tunnel is more than 800 feet long, but let's say just for numbers, simplicity of numbers, we take 800 feet long tunnel with doors on each end, which can be used to seal the tunnel. In other words, you have, let me show now the picture. You have a tunnel. We have already made it, constructed it, that it is 800 feet long, and it has doors. And the doors are, controlled by the people on the ground, such that it will open and close according to your command, right? You press the thing and it will slide open and close, open and close. All right, so here's your tunnel. You have built it for 800 feet. But now There's a train coming. The train itself is 1,000 feet in its own rest frame. So this is the proper length, okay? The train itself is 1,000 feet. So this picture shows the train itself is longer than the tunnel. So then you say, gee, what are you trying to prepare me for? I know, certainly, this train cannot be trapped inside this tunnel. And yet, Herr Professor Alberto Einstein, right? He now has this Gedanken experiment. He now says, what if the train is moving with a velocity which is, I forgot now what it was, let's say 0.6 or something, or 0.8, the speed of light. Supposing the train is really moving very, very fast. Not that there is any train that does that in our real life, but Gedanken experiment is supposing what would happen if I could have a train that really moved so fast. Okay? So first thing is, you now say, if the train is moving very, 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 very fast, what is this Lorentz contracted length as measured by the guy on the ground? Because this is, I'm on the ground and you are a spaceship. You are a train that is like a spaceship, and you are yourself 1,000 feet, but you are rushing. Then according to the formula, and here we will call on the formula. The formula is, what is your proper length? That's 1,000. And you now multiply by the contraction factor, 1 minus v over c whole thing squared. Now, if you were moving with velocity 0.8 times the speed of light, then this would be 600 feet. I'm already making use of Lorentz contraction, and I'm feeding in what you told me. Well, I haven't yet told you, but in the next slide, I will tell you that it is coming by at 0.8 times the speed of light. And if that is the case, then I already remember what you have taught me on Lorentz contraction, and that therefore the Lorentz contracted length as measured by me, I am on the ground, I will see that you are shorter now. Shorter by a factor of square root of 1 minus v squared over c squared, and voila, that is 600 feet, because 0.8 is 0.64, 1 minus 0.64 is 0.36, that is 0.6, therefore it is 600 feet. All right, so now I already know that you, even though your length is 1,000 feet, but when you are moving so fast, according to Einstein's theory of relativity, you will now have a apparent length that is shorter. Your apparent length as it I can measure, that I can measure on Earth, on my ground, because you're moving by, and that is now 600 feet. All right, are you comfortable with what we are doing now? I sort of got immediately this concept that you are asking for Lorentz contraction. Then I look up the formula, and then I just have to know what to use it, how to use it. And since you told me that its own proper length, its own length in its own rest frame is 1,000, and I didn't tell you, but the spaceship or this train is moving with 0.8 the speed of light. Boing, the actual length of this train is now shorter. It's not 1,000 feet, it is 600 feet.
Professor, we cannot hear you. Professor, we still can't hear you. We still can't hear you.